Lecture 21, we are going to study how learning can be done in Markov logic and how can we use Alchemy for learning. Okay, so let's start with a very general introduction for introduction to learning. So what we are going to utilize is MLE method. So for those, how many of you are familiar or not familiar? How many of you know what is MLE? How many of you don't know? Okay, so some people. Okay, so let's recap what that is. So likelihood is the measure of quality for different parameter values. And what we want to do is to find the parameter values that maximize the likelihood. And this is called MLE. I'm going to actually talk about the example which makes a bit more clear. So for instance, you are given a coin and you see you toss the coin for 100 times, and 2/3 of the time that the coin is head and 1/3 coin is tail. Is this coin fair or biased? What is your expectation here? It's kind of biased, right? It may be also a fair coin, but there is some chance that this is a biased coin. What we want to know is, given the data, we want to find out what is actually the probability of the coin to be on the head or tail. Okay, so before we are doing the inference where we already know the probability distribution, from then we want to find what is the probability that we will get 66% of coins to be head and 33.3 whatever percent is tail. What is the probability? So you can compute this probability, right? So you're given the probability distribution and you have to explain why the data, what is the probability of getting this data. Now learning is actually opposite direction. You're given actually the data and you don't know the probability distribution underlying it. So you have to find out what is actually the parameter for this probability. Okay. So if you have this kind of thing, so suppose you have some parameter theta that you don't know maybe the distribution there or probability distribution there, but you know something about the observation. So let's say you observe some data x1, x2 up to say xn. Okay, and you don't know what determines this data distribution. So there's some underlying parameter. So it's like a bias in the coin. That probability could be a theta. Now, if you have that parameter, and assume that all the draw is independent and identically distributed, which means that you're getting the head in the first has nothing to do with getting the head in the second. Okay, so each event is actually independent. So then you can write this in terms of multiplication of these individual instance. Okay, so okay, I'm going to actually use semicolon because people often use bar there, but it may be confusing with the conditional probability. Okay, so this semicolon means that the parameter of this f is actually x1 through xn, but it is actually kind of conditioned on this parameter theta. Okay, so as I just said, if you already know the theta value, then you can find out the probability of the coin being tail, head, tail, right? So you can figure it out. Now, likelihood is actually the opposite way to look at the same function. So instead of fixing the parameter and finding how the data is derived, we are actually, let's use actually different function name. Here we are observing, say, the data, and we want to find theta value. Okay, so here is exactly the same function. It's just that what we want to view as a varying things. So x1 through xn are now fixed. So you are given this data. Data is fixed. But what theta will best explain this data? So which value of theta that you want to draw? So this is exactly same function as this. We are just looking at from the different angle. Okay? So let's actually look at the example. Okay? So now we flip a coin. We get head, tail, head. Before you actually answer this question, let me ask you, if this coin is not biased, okay, it's a fair coin, then what is the probability to get HTH? 1/8, right? So each of them are independent. So 1/2 is for the head, 1/2 for tail, 1/2 for the head, right? So you just multiply those things. This is actually how you utilize the first equation. But now we want to do the other things, okay? So we are going to fix these data. So HTH is actually fixed. Then what is actually the best explanation about the probability of coin to be on the head? Of course, this is not a significant data, but let's assume that, let's use our intuition. What is the probability of getting the head? 2/3, right? So 66%. So how do we compute this? Well, roughly what you do is, of course, you use common sense here, but if you assume that this probability to be on probability of head is p, then this data can be explained by p times 1 minus p times p, which is p square minus p cube, right? So p square minus p cube. Now we want to find out the value of p that maximizes this likelihood. So this p square minus p3 is actually the likelihood, right? What is the value that maximizes this p? The value. What is the value of p that maximizes this p square minus p cube? So that's actually the 2/3. When p is 2/3, this value gets the maximum. Okay. All right, so that's actually the intro, and we are going to see how you use maybe derivative, as somebody just said. So we'll talk about that soon. Okay, so one thing that we want to utilize the likelihood in MLN, we are not going to, so actually, let's say, what we are going to do is we are now going to fix the data and then try to learn the parameter. So what we are going to learn here is actually the weight of the formula. Okay? So before we are fixing the weight, and given this weight, what is the probability of this formula to be true? That's an inference. But now you're given the data, and then you want to find what is the weight that can be associated to the formula, so that best explains this data. That's what we are going to do. So we are going to learn the weight. And for the Markov logic, we know that the weight scheme was using the exponential function, so it's much easier to manipulate with log likelihood. So instead of the main function, we are going to use log linear model. So okay, so what is the general log linear model? We had something like px, let's call it w. So w is actually the parameter theta in the previous slide. And log linear model has this form where we have 1/z, z is a partition function, and we have exponential of all the I and wi, fi, maybe some di. So I'm talking about the general Markov net, where you define the potential function in terms of the weight and feature. Okay, it should be familiar to you. Now, what we will say here now is this z is no longer a constant, because when you change the w, z also changes, right? So z will now be a function of w, okay? Because here we are not going to fix the w, we are going to learn the weight that maximizes it, okay? All right, so this is the log linear model, and log likelihood function here is just to put the log on top of this, right? So log of px So what does this function look like?
Summation of WI x.
So I assume that you're familiar with calculus, right? So if you have log of the fraction, so what do you get? Log of the enumerator, numerator, okay, minus log of this, right? Yeah.
Should that be di or x?
Di is actually the potential, so the part of x that participate in the click. Okay, so if you are curious about that, I can actually change it to xi, which was probably the one that we used in the previous slide. Okay, note here that the feature doesn't have to necessarily cover all x, so it's a part of the x. Okay, any other question? Okay, good. So let me also change that to xi. So this xi is actually not the individual x, but it's a part of the x that forms this clique. Okay? And obviously log and exponential cancels out, so then you get this. Okay? Now this is actually for single data, because I fixed one particular x. X is just a single interpretation. Okay? And in fact, in Markov logic, we are going to actually learn the parameter only from the single interpretation. Okay? And even that is actually a very powerful thing to do. Okay? Any question up to this part? All right. So I may confuse you today if I start from derivation. Okay? So let me know if some step is not clear. One thing to note here is log likelihood function is concave. So what concave means is basically it is, if it is 2D, it looks like this is going upward. Okay? If it is, maybe you can also draw this way, where here is actually the highest region. Okay? So this is concave, which means that there is any local maximum is actually the global maximum. So you can just use standard gradient ascent method to find this maximum value. Okay? How many of you don't know what is gradient ascent? How many of you know what is gradient ascent? And the rest don't know whether you don't know gradient ascent. Okay. All right. So I have some quick slides for that. If you are curious, you can actually look at some other references. Okay. All right. So and basically the idea is very simple. So I can just explain in one slide. So for the log likelihood for the log linear model, since this is a concave, you can just iterate some steps. And basically the step is very simple. Let's actually look at the 2D like this. So suppose you are at this side of the hill. Okay, so let's say this is actually where you want to go. This is actually the value of the parameter that maximizes this function. So I want to find out this value, say p. Okay, but right now I'm in, say, p prime. Okay, what I can do is I look at the gradient of this function, and the gradient is actually going upward. Okay, which means that this is not yet the maximum. So you actually climb a bit. Okay, and then check the gradient again. The gradient is actually slow. The derivative is actually smaller than before, but it is still positive. So then you actually repeat going for the step to the right until you hit maybe the gradient to be 0. Okay, or if you are here, then gradient is actually negative, right? So it's actually going down. So then you have to go this direction to go here. So regardless of where you start, if you follow this gradient, you can find the maxima. That's the basic idea. Okay? So what do we do? Let's just initialize the weight with maybe arbitrary weight for the beginning, and repeat the following until the weight converges. So the equation is actually very simple. So for each of the wj, so wj is a weight, okay? you just add this value to the current weight, okay, until the weight does not change much. Okay? So what is this thing? This lambda is called learning rate, which you can actually give different values. It's like how long should be one step. If it is very big, then you actually jump big. If it's not, then you go slowly. And this is a partial derivative of the function, the partial derivative log likelihood with respect to the current weight Wj. Okay? So many of the machine learning algorithms can be actually computed by gradient ascent method, especially neural network. This is actually the standard method to use. Now, some people, usually more often we call it the gradient descent method because we want to minimize the loss function. But for the sake of this class for today, we don't have to go that route. We will just call gradient ascent. Okay. All right, and basically the same as the gradient descent of the negative of the log likelihood. Okay, so that's the equivalent thing, but you don't have to make more complicated than necessary. Now this method works well for some cases where we cannot simply find closed form solution for the problem. So for instance, here when we talk about this question, we can actually quickly find the solution even without using gradient ascent method. If you use the derivative of this function is 2p minus 3p squared. And that value, of course, p equals 2 over 3 is to what then makes this derivative to be 0. So there is often, if you can find closed form solution like this, then you don't even need to do use the gradient ascent method. Unfortunately, this is not the case with Markov logic. There is no closed form solution like this. So that's why you have to use some iterative method like gradient ascent. Okay? Okay, we actually didn't talk about Markov logic yet. We are just talking about the general introduction to gradient ascent method. Okay? So here is one example of gradient ascent. So this is the same function that you see, p squared times 1 minus p. And if you draw this function, it actually look like this, but if between 0 and 1, it actually works like this. Okay? So we'll just look at this portion. And of course, derivative is actually 2p minus 3p squared. And I use Excel to just compute this. So if just simple function, you can demonstrate. So initial value is 0.4, and the gradient is actually 0.32. So it is something like here. The gradient here is actually 0.32, which is still positive. Okay, so you have to move. Now, the learning rate is 0.5, which means that you multiply this number by 0.5, which gives 0.16, and add it to the previous value of p. So that I can get 0.56. And at 0.56, which is probably somewhere here, compute gradient again, which is 0.1792. Okay, and multiply by 0.5 and add it to the previous value here. So 0.5 times this value plus the previous value will give 0.57. Okay, and you repeat over and over again. And as you see, the gradient here goes down. It gets smaller and smaller. And p gets actually bigger and bigger. I actually didn't go through all the way, but at 0.66, you can find out, of course, this gradient is 0, and we can stop there. So that's actually somewhere here, which is the maximum value. Okay, very pretty simple. All right, any question up to this part? Okay. All right, so now let's talk about how to adapt this idea to the Markov logic learning. So in Markov logic, we will get the data, and we'll assume the data is a relational database, which can be given as a set of facts as in what we did in ASP. Okay. And for now, assume we say that this database that you give as an input is actually understood as a single interpretation. Okay? Note here that database, in the relational database, the concept is you can enumerate all the positive fact as a set of positive relation as a set of fact, right? And you can also view this set of fact as an interpretation. Okay, so you can identify the database with an interpretation. Are we together? Okay. So we're actually going to see a simple example, but just want to give a brief recap. There are different learning problems here, and we will not actually go over all of these. If you're interested, you can take a look at the reference that I posted on the Blackboard. We will focus on actually the learning parameters. Okay, so we are going to use some method that we know from the Markov network learning, which is actually the advantage that Markov logic network has, because it is defined as a template for Markov networks. In principle, the algorithm developed for Markov network can be used for Markov logic. Okay. Now there is another thing which I will not go into detail. I mean, which we are not going to study in this class. But if you're interested in, you can actually learn the formulas itself. Okay. So in the first case, let me just recap. So here, the learning parameter means that I give the formulas, but I don't know the weight of the formula. And if I supply the data, then the learning system will learn the weight of the formulas that explains this data. Now the user actually gives the formula here. But the more ambitious goal here is to actually let the system come up with the formula together with weight. So you just throw the data and the system will just learn the rules and the weight automatically. Okay? All right. Okay, so here's a quiz. So be prepared. So without saying anything to you, but just given the intuition that we just talked about, which is the best explanation for this data? And let me open the Socrative. And this is actually a multi-choice question, so we'll see how it goes. Okay, so these are the formulas. W1 has a variable py, and I give 3 formulas here, and you have to choose one of these 4 possibilities. I actually didn't include W1 because of the reason that I will explain later. Okay, I'll give you 1 minute to think about. Okay, are we done? Let's look at. Let's see. Okay, interesting. 75% is A. 13% is C. How come this happened? Okay, so majority is A, the second is C, and then D and B. Okay, let's see whether this is the case. So let's, actually what a stupid question that I asked. I didn't give you the data. Oh my, okay. Let's do this again. Okay. I mean, how can you do that without having the data? Okay. I'm sorry about the confusion, but you should have asked me, where's the data? Okay, let me open this again. So the data is here, okay? So note here that the exclamation means it's a negation. So P1 and P2 is true, P3 and P4 is false. What is the best assignment to the weight that explains this data? In other words, if you think about the intuition, what is the value of W that gives highest unnormalized or highest probability to explain this data? Or let's say this way: what is the value of the assignment to the weight so that this interpretation gets the maximal value, maximal weight? Okay, so shall we? Are we still? Okay. Let's see. Okay, so the majority is now C, followed by A, B, and D. Okay, good. Let's see why this is the case. If you look at the formula, let's see what formulas are actually true and what are false. So forget about W1 for now, but what is this one? Is it true or false? This is an interpretation. Remember, data is an interpretation. Does this interpretation satisfy this formula? Yes. What about this one? No. What about this one? Yes. So according to the intuition, we want to maximize those weight. That is actually true. So W2 and W4 should get the same, means highest weight here. Okay? All right. So of course, I didn't actually introduce the formal details, so let me do that now. Okay, but the answer is actually C here. Okay, so we'll talk about two different types of learning. First is called generative learning, and the second is discriminative learning. Okay, what is generative learning? It's basically what I just told you about. It's about maximizing the likelihood of the interpretation. Okay, and I'm going to talk about the discriminative learning soon, but that's actually very minor modification to this. In principle, the database that you consider may encode multiple training examples. But for now, we'll assume that this represents a single example. Okay, as in the previous thing, this is a single example. Okay, now we are going to learn the weight from the single example. And the likelihood of the random variable x is given by this formula. Okay, nothing special. The only difference from the previous one is the feature is fixed to be the number of formulas that are true under the interpretation X. Okay, that's the only difference from the general setting that we just saw versus the Markov logic setting. Okay, so this is actually Markov logic thing. And in the same way, you actually can see that log likelihood of X is given by this formula. And all you need to do is to find the value of W that maximizes this value. Okay? Note here that this W, which is also in the Z, they are not fixed yet. Okay? What value of W that you want to assign so that this whole likelihood value is the maximum? That's the goal here. Are we together? Okay. Okay, so how do we compute gradient of this log likelihood? This is a bit complex derivation, so let's actually do this carefully. So we are going to look at the gradient of this log likelihood function with respect to some particular weight Wi. So this is Wi, partial derivative with respect to Wi of log of okay, so okay, so we'll look at the gradient of this log likelihood. Okay, so what is the partial derivative of this log likelihood with respect to Wi, a particular weight of Wi? So that is just unfolding the definition. We have to replace this, but let's see. We can distribute this derivative, so which gives okay, and the first term is actually simple. This is actually sum of all the W1 and 1 plus W2 and 2, W3 and 3. But we are differentiating with respect to Wi, so this will give only the coefficient of Wi, which is Nix. Okay, and the next one is derivative of the log will give 1 over Z, and then the derivative of Z. Okay, good. Now what is this Z? Z is the normalization factor, and that is for the whole interpretation, what is their weight. So we add up all those things. So this is Z. So I'm going to unfold this definition. So this will be Nix minus, so 1 over, let me actually use x double prime to range over all the interpretation. Okay. Okay, so this is 1 over Z, and then I have this part. Now, actually, let me just write here. This is derivative of the Z, the same Z. But this time, for the reason that will be clear, let me use x prime to range over all those interpretations. Okay, so that gives me the same one. Okay, so we have x and x double prime and x prime. So if we look at this derivative, this is the sum of exponential functions, So the derivative of this will give the exponential function, and then derivative of the argument of the function. So this will be is copying, and this part becomes now the function inside the same function. Prime. But then we have to multiply with the derivative of this inside. That will be that is actually nix prime, same as what we did before. Okay, so we have derivative of the whole, which is just get this one, which was right here, and then derivative of this one multiply, which will give nix prime. And then what we write here is nix minus. I'm going to slightly rewrite the numerator, because now the z part in the denominator is actually the constant. So we can actually have x prime here, and then write the numerator here, multiply by nix prime. Okay, I think again I'm running out of the space, so let me just change the color. Okay, so what is this whole thing here? Okay, if you look at this, by definition, this is the probability of the interpretation x prime. Okay, so the blue part is same as PW under the current interpretation, current to weight. It is x, the probability that x has the value x prime. So the whole thing here can be written as nix minus the sum of x prime pw x equals x prime multiply with nix. Okay, and this value is actually the expected number of ground formulas that are true under this Markov logic network. Okay, so you will see in the next slide. Okay, so what we actually compute in the previous slide is actually this equation. Okay, so I mean, if you didn't follow some part of the derivation, it's okay, because it's actually complex derivation, and I shouldn't have studied that here. But I will actually give the derivation in the slide, type in this derivation. But basically the message is this: the gradient here, although it's a bit complicated to compute, is actually the end result is very simple. Okay, so this is actually what you get in the previous slide, and what it means is this part is expected value, is expected number of ground formulas that are true under the interpretation. Okay, so let me actually recap. So what are the things that we have now? The first term is number of ground formulas that is obtained from the ith formula that is true under the interpretation x. Okay, so let me repeat. So x here is the database instance that we are given as a single interpretation. Once we know the interpretation, we can find out how many ground formulas are true under x. And we are not actually looking at the all ground formulas, but looking at the ground formulas that come from the ith formula. Each formula may have a variable, and we are only counting how many ground instances of ith formula is true under the current interpretation x. That's what nix is about. Okay, The next thing is this. We are going to do with all the values of x prime, not necessarily the current database, but all possible values, all possible interpretations. But we are going to multiply this with the probability of having that data, which gives the expected number of ground formulas that are true under the interpretation, under this MLN. Okay. All right. Let's actually look at an example. Okay, but before we do this example, I just want to make sure that you follow what is this expression. Okay, so just remember this, and I'm going to show an example in the next slide. Okay, so NIX. Note that in MLN there are actually multiple formulas, right? Let's look at only ith formula. Okay, ith formula is maybe non-ground. You may have a variables. Okay. Now, given the database, given the single interpretation in the database, how many ground formulas coming from this ith formula is true under the interpretation? That's what NIX is representing. Okay? And this value is actually not just for this particular interpretation, but for all interpretation. What is the expected value of the ground formulas coming from this that are true? Okay? So try first interpretation. And that gives me how many ground formulas are true under that first interpretation, right? Now this this first interpretation may be associated with certain probability. So what is probability to have the first interpretation times the number of ground formulas that are true under the first interpretation. And we repeat this for all the other interpretations. Okay? Okay, so let me actually show you the example. Okay? So this is the same example that, no, not the same. It's actually a bit simplified example. I have only three formulas here. Okay, so P of X is a ground, non-ground formula. X is a variable. The second and third are ground formulas. Okay? And according to the gradient Ascent method, we are going to update each weight according to this equation. Okay? So if you don't know what was the derivation, forget it. Okay? But just focus on the meaning of this gradient. Okay? So we are going to update each weight by this term. Eta is the learning rate, you can set it. And this is the gradient we just talked about. The current, what is the, how many formulas are true under the interpretation X. And this is how many, what is expected number of ground formulas that are true. Okay? So having that in mind, let's actually look at the example. Okay? So if we have three atoms like P1, P2, P3, then we have 8 possible interpretations, right? Okay. Now suppose our data is P1, P2, and not P3. Okay, so suppose you give this as a data, which I'm going to denote as 110. Okay, this is a single interpretation. Okay, now N1X means look at the first formula and consider all ground formulas that can come from the first formula. How many ground formulas there are satisfied by the interpretation 110? Okay, so just look at this one. This is the first formula. How many ground instances of this formula is true under this data? So first there are 3 ground formulas, P1, P2, P3, that can come from the first formula here, right? And among them, 2 are true and 1 is false. Okay? So N1 of X here, okay, is 2. Okay, this is the value that we plug in here. Okay, the next value is actually very difficult to compute, but since this is a small example, I actually generate all of them. Now, let's not only look at this interpretation, but look at all other interpretations. So there are 8 possible interpretations, starting from 0, 0, 0 to 1, 1, 1. And each of these interpretations has a probability, right? According to the current weight. Okay? So you are given this current Markov logic. So you can find the probability of this interpretation under the current Markov logic, right? That's what you did in the inference. How do you do that? Well, e to the power of all the sum of the weight that are true, right? Divided by the normalization factor. So I'm going to skip that part, but this is actually the value that I compute. Okay? Now, with this, I can also look into how many, if this was the interpretation, how many ground formulas coming from the first formula is true under the first interpretation there? Nothing, right? Because now the interpretation says all are false. Okay? So the ground instance of this is P1, P2, P3, but none of them are true under this interpretation. So N1 value for this is 0. Are we together? We can do the same thing for 0, 0, 1. For 0, 0, 1, how many ground formulas are true from the first one? 1. Okay? And the probability of that interpretation can be computed to this, and you can actually finish up all these things. Are we together here? Can you actually write this table? If I give you this as a homework, can you do that?
So what was the choice of W initially? What was our choice of W? So how to compute the probability of W?
Okay, so we'll get there, but I just want to make sure that everybody followed this table until now. Okay? Okay, so let me actually go continue. You actually compute everything, okay? Then you can find expected value, which is just the sum over all these things, right? So this one gives the probability of having the first interpretation multiplied by N1 is N1 value. Okay, this is the respect to second interpretation and so on and so forth. So if you add up everything here, that's actually the expected value of N1. Okay, and that is actually 2.7941. Okay, so that is 2.7941, and assuming that the eta is actually 1 and initial value of W1 was 1, this is actually the value that you are going to compute, and this determines the next value of W1. Okay, are we together? Yes. Which color? Probability of interpretation can be computed by the definition of Markov networks, Markov logic. So you can go back to the previous slide, but it was probability of x equals e to the power of I, wi, and ix divided by the normalization factor. Okay? Yes?
Calculating set explains will be all the interpretations like that, and I'm not sure what the weights would be. Could you just explain what that would be? Like
So
I'm trying to
which one?
find out what Z is.
There is no z here. So why are you talking about that?
Like when we're trying to find P of X equal to nothing over Z.
Oh, that is actually the inference thing, which I don't discuss here. But that can be computed by adding up all these things for different x.
So the weights would be 1 over here? That's what I'm not sure about.
This is the probability of the interpretation, right?
Yeah.
And we are talking about the weight of the rule,
Okay.
right? So initially, I just randomly gave, not randomly, I just gave the weight to be 1, okay? And I'm going to update this,
Right.
okay? right? So with the very first iteration here gives me that W1 was too high. Okay, you have to update to 0.2095. Okay, let's look at actually the next one. Okay, that is about the second weight. Okay, so this is actually, we are going to do this in parallel, so we are not actually updating the W1 yet, okay? But W2, assuming that this is the current weight, W2 will be updated by the similar equation, okay? So here you can see that 110 is the current database, right? So now we have to look at the second rule. How many ground instance, well actually it's already ground, but how many rules coming from the second rule are true under the current database? There are only 1 or 0, right? The second rule is either true or false. Okay? So 110 means P1 and P2 are both true, so it satisfies the second rule. So the number of ground rules that can come from the second rule is actually 1. Okay, and this one rule is already true under the interpretation. So this is actually 1. Okay, but you can also repeat this with respect to all other interpretations. And each of them will give whether this each of them satisfies the formula or not. If it is satisfied, it gives 1. Otherwise, it gives the value 0. And besides, you can also compute the probability of having that interpretation under the current weight, which is the third column that you see. And then you can compute the expected number of ground formulas that are being true. And that gives me 0.9937. Okay? So the update will now have 1 plus, this is actually current value is 1, eta was 1, and N2x is coming from this is 1, and this value comes here, 0.9973. Okay, so then you get this thing. Okay, and you can repeat. Are we together? Yes?
How much is the learning rate?
Learning rate was just arbitrary here. Yes, there's a hyperparameter you can set separately. Yes. Obviously, this is artificial example. Running rate 1 may be too high here. Okay? And yeah. Okay, I just want you to be familiar with this method. And good news is, of course, you don't have to compute by hand. But I want you to get the feel how complex is this update. What is the bottleneck of this computation?
Probability computation. Expectation.
So it's pretty simple to compute N1 value, right? So you can just see how many ground instances are true, although it's not really that simple. In reality, it's actually also a complex problem. But finding the probability, you have to find the normalization factor. Okay, that means you have to do the exhaustive listing. And that is actually very time consuming. Okay? All right. And this is actually the updating the value for the third rule and so on. Okay, so here is actually the running example. Actually, I can show you how to do. So this is the simple example encoded in the syntax of Alchemy. So you declare num to be 1, 2, 3, and P of num is a predicate declaration, and then we have these 3 rules encoded. Now, this time we have to supply the database. So ex.db contains this interpretation. Okay? And now you're going to use this command line to compute the weight. Now here I gave the just 1, but this is not the weight that explains the data best. Okay, so we are going to use the tool to compute this weight. Okay. And maybe I was idle too long. Okay, let me just go back. The next homework will involve using Alchemy, and it actually runs on the Linux machine. How many of you don't know how to use Linux?
I know how to install Mac.
Oh, you can install on the Mac. Oh, that's a good idea. Actually, I don't know how to do. So I'm just logging into my lab server. But if you know how to do, why don't you share that information on
Sure.
the Piazza? That will be helpful. Thank you. So you can run on the Mac too. We just learned. Good. Okay, so this is ex.mln, and this is ex.db. So how do we do this? This is learn ways, and we have to give the input and output of the learning. So let's actually say, so the output is actually the MLN file. Okay, it will be very similar to the given input, except the weight will be updated. Okay, and I'm going to use the training example to be the ex.db, and this is called the query predicate P. Okay, so I'm going to explain this last option later, but if I do this, okay, it'll do a lot of gradient ascent iteration, and it computes at the very end. Okay, so the outcome is actually the this one. Okay, so as you see, this is similar to the one that we saw before. The input actually has norm equals 1 to 3, but the output file doesn't actually need that. So there are actually 3 rules in this program. And for the first one, it learns the weight to be this one. Now, A1 is also a variable, okay? And for the second and third, it actually gives this. Now, as you see, this database had P1 and P2 are true, but P3 is false. So under that assumption, this formula should not get a high weight because this formula is violated. Okay, so that's why it gives the negative weight here. While P1 implies P2 is actually true, so it gets a reasonably high weight. Okay? All right, so that's how you do. Right. So this is output. Okay, so one thing that I don't want to actually go into the detail, but I just want to tell you, computing the probability or expected value is actually very hard. It's actually intractable, and because of that, the actual system uses pseudo likelihood instead of the actual likelihood. And this is something that is close to what we discussed before. Instead of the likelihood as we saw before, we are going to simulate this with this function. So it's a multiplication of each random variable x gets some value given its Markov blanket. Okay, and as we saw before, if you know the Markov blanket, then it becomes actually quite simple to compute this probability because you only need to compute these 2 values. Okay, and that is actually much easier to compute than the whole expected value. Okay, I'm not going into the detail here. If you're interested, you can actually follow these things. Unfortunately, this method actually does not work well when the dependency chain goes long because it's not actually something that can be easily covered by Markov blanket. Okay, so the value becomes very distorted if you have more complex dependency. Okay, but there is actually a trade-off. If you want to compute the given one, that is actually hard to compute. So you have to wait for a long time, while this one returns the value quickly, although it is not very correct. Okay. All right, so I'm going to now talk about the discriminative learning. So the concept here is we want to distinguish between some atoms that are evidence. So we assume that some atoms are always known to be the evidence, and we don't carry over the probability. Okay? So there are many applications that this is actually fixed. So if, for instance, in the collective classification problem, you want to compute the probability of the class given their attribute. Now, attribute is actually fixed. You don't want to learn the weight of the attribute. In that case, you can designate this attribute as evidence predicate, and you can only focus on the query predicate. So what that means is, instead of the likelihood that you saw before, we are going to maximize the conditional likelihood, where this X, the evidence, has already fixed value. And we are going to only maximize this, the conditional probability of Y given this X. And this actually works well because we have less parameter to learn. Okay? In terms of the equation, this is actually pretty similar, except that now the normalization factor should be only those that is consistent with the evidence. Okay, so when you sum up all the weight of the interpretation, you don't do that with respect to all interpretation, but only look at the interpretation that is consistent with the evidence. That's what this subscript X is saying. In the same way, this NIX in the previous slide before is replaced by NIX, comma Y. Here, Y is actually the query value, the value that we want to compute the probability, and X is the evidence. So NIXY is the number of ground formulas that is obtained from the ith formula, and is consistent with the assignment X equals X. Okay? All right. So in descriptive learning, what is the function that we want to optimize? It's a log likelihood of the conditional probability. So it is okay, and as we saw before, this is this one. Okay, and obviously to optimize this, we can actually do better or easier if we do the log likelihood of this conditional probability. So that is this one, which will be okay. So then the gradient here is gradient of this log likelihood, and I'm not going to show you the same derivation as before. It's actually pretty similar to the previous derivation, except that we have now the evidence variable. So here you can derive in the same way as before. This is let me just write the thing, sum of all those conditional probability for different Y values given X multiplied by okay, the sum is going over this. And if we write one more step, this is same as expected value of Y prime, the number of the ground formulas that are true from the ith formula. Okay. Okay, let me go through a few more examples. So, learning multinomial distribution. So here we have the dice, and we throw 20 times, and each dice can return either one of the value from 1 to 6. Okay, so how do we learn the weight of this? Now this time the data will be given to us, and it's actually some bias distribution. Okay, So this is how you're going to do. This is actually the input file, okay? And you don't actually give the weight. You can give the initial weight as I did before, but you don't have to do. So you just write these formulas, okay? So here we are given outcome T1, means I want to learn the weight of this formula. How much, how likely to get the phase 1, and same for the others. And the data is actually here. And as you can see, it's actually quite biased. Most of the time it returns, actually always it returns either 1 or 6. Okay? So what do you expect the weight to be? Obviously these two should get the highest weight and all the others should get the low weight. Okay? So let's see how we do that. Did I have that? No. So it's actually not a very complex example. It has only 20 throw, but it takes this much of time. Now, of course, you can actually control this runtime. You can see that these iterations are repeating, right? So as in the gradient descent, you can actually set this iteration to be a particular number, okay? Or even in the sampling that is actually internally used using MC sets, you can change the parameter there. So you can actually change the timing. Sometimes you can also give the maximum number of seconds to be run. So then the Alchemy will check whether it exceeds that time threshold. And if it is, then it will just terminate. Okay, so I didn't actually give any restriction, so it will just run this much. But as you see, it's already pretty close. The first one and the last one has the highest weight, and the others are getting low weight. Okay. Okay, let me kill here because that's actually not the best way to compute these things. In principle, we know that each throw will have exactly one phase, and I didn't specify that in the previous run. So if I give this thing that exclamation mark means that each throw will get exactly one value, right? Maybe I already did that, I remember. Oh, actually, I already did. Okay, so sorry about that. So it's just the same thing as before, but instead of writing these multiple rules, we can write this one rule where you see this plus. Okay, upon seeing this, it will expand this line into 6 lines depending on the values of f. So here f has 6 values, so it will be replaced by T1, T2, and so on. Okay, and then learning will be done here. Okay, to learn the weight of this. This notation is actually handy when you have a lot of instances there, so you don't want to actually enumerate all those predicates. Okay. Okay, so if you do that, this is actually the final outcome that you learned. Okay, for the smoking example, we already talked about this, but here this time we don't actually give the weight here. Okay, and we use the same mechanism to do that. And here we give the training data. And this is a small training data. Okay, so friends and smokes and cancer relation. And if you do that, the final outcome will be these things. So it will learn this weight. Okay. Okay, any question up to this part? So I know the derivation of the equation was a bit confusing, so let me actually type in and post it, post that slide so that you can follow. But even if you don't follow the derivation, it's okay. Something that I want you to understand is the meaning of the gradient. Okay, so what is that term in the gradient means, so that you can actually compute by hand if needed. Yes?
In the previous slide, we had the outcome, the one before this. We had the rule where we said outcome t comma plus f.
Right.
In there, how does it correlate the plus f with the faces? Does it figure it out from the examples or from the previous?
So how do we know which value that it has to instantiate? I don't know particular about that algorithm, but I presume that Alchemy is actually good at finding the domain. So if you have given this way, then obviously for sure that you have defined outcome as a predicate that has face as a second argument. Okay, so then you can actually look into this value to populate this.
So because that second rule is there, right?
Yeah, this one?
Yeah.
This one is a declaration. So yes, Alchemy knows which values to use for that argument, yes. But sometimes I do see that this is actually not needed. Alchemy can actually look into the database to grab those values. Okay? Yes?
Professor, in this example, what are the evidence and what are the truth?
This was actually generative learning, so you don't have to worry about that. But even if it is this, if you look at this as a discriminative learning, if you make the evidence to be empty, then this is the same as that. Okay? Right. Any other questions? Otherwise, let me open